Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Before there were batteries, there was only the moment. Light existed when the sun was overhead, when fire was burning, when candles had wax left to consume. Work happened in rhythm with daylight. Conversations ended when darkness made faces invisible. The night belonged to rest because there was no portable way to hold energy, to carry power from one place to another, to store it for later use. Energy was always tethered to its source, inseparable from the thing producing it. The limitations shaped everything. Cities were denser because people needed to be near their work, near sources of heat and light. Factories ran only during daylight hours or burned through enormous quantities of fuel to extend operations into evening. Communication over distance required messengers, physical bodies carrying written words across landscapes. The speed of information was the speed of horses, of ships, of human footsteps. Nothing moved faster than muscle could carry it. Early experiments with electricity revealed something tantalizing. This invisible force could make things happen at a distance, could travel through metal wires, could produce light without flame, could create motion without steam or muscle. But electricity in those early demonstrations was momentary, fleeting. You could generate a spark by rubbing materials together, create a brief discharge that made hair stand on end or gave a mild shock. The effect lasted only as long as the action producing it. When you stopped rubbing, the electricity vanished. Static electricity could be accumulated in glass jars, layered with metal foil, creating primitive capacitors that held charge briefly. These devices were curiosities, parlor tricks that demonstrated principles but had no practical application. The charge leaked away quickly, dissipating back into the air, into the glass, into whatever materials happened to be nearby. You couldn't rely on it, couldn't use it for any sustained purpose. The storage was too temporary, too unstable, too dependent on conditions that were difficult to control. What was needed was a way to capture electrical energy and keep it, to bottle it like water, to carry it from place to place without it escaping. The device would need to hold the charge stably over time, release it on demand. Do this repeatedly without degrading. It would need to be portable, reliable, consistent in its output. The requirements were clear even if the method for achieving them was not. Chemists and natural philosophers understood that electricity and chemistry were connected, that certain reactions produced electrical effects, but translating that understanding into a practical storage device remained elusive. The telegraph was coming, though it didn't exist yet in functional form. The idea was there, the concept of sending signals through wires over long distances. But signals needed power, needed a steady electrical current that could be controlled, turned on and off precisely. Generators existed, but they were large, stationary, dependent on constant mechanical input. What the telegraph would need, what dozens of emerging applications would need, was electricity that could sit quietly waiting, ready to flow when required, independent of any external power source in that moment. Medical devices were being imagined, theoretical applications of electrical current to treat various ailments. Researchers had noticed that electricity could cause muscle contractions, could stimulate nerves, could produce effects in living tissue. But to use electricity therapeutically required a controllable source, something that could deliver measured amounts of current reliably. The sporadic discharge of static electricity was useless for this purpose. The vision of electrical medicine waited on the development of electrical storage. The gap between what electricity could do in theory and what it could do in practice was the absence of the battery, though no one called it that yet. The need existed in outline form, a shape waiting to be filled with specific chemistry, specific materials, specific design. People who worked with electricity understood the problem intimately, felt the frustration of generating power that immediately dissipated, of having to produce electricity at the exact moment it was needed, rather than storing it for later. Lighting was perhaps the most obvious application waiting to be enabled. Candles and oil lamps were expensive, dangerous, inefficient. They produced as much heat as light, filled rooms with smoke, required constant attention to prevent fires. The flame was delicate, extinguished by drafts, consuming oxygen from enclosed spaces. Workers in mines carried open flames into environments filled with explosive gases, a necessity that regularly resulted in death. An electrical light source would be safer, cleaner, potentially more reliable. But it required steady power, more than a momentary spark could provide. The problem of timekeeping could benefit from electrical precision. Mechanical clocks required regular winding, their accuracy dependent on the consistency of spring tension or the swing of pendulums affected by temperature and humidity. An electrical clock could theoretically maintain more consistent time, driven by the steady pulse of current rather than the gradual unwinding of stored mechanical energy. But without a way to store electrical power, such clocks remained theoretical, sketches in notebooks rather than working devices. Portable communication was impossible without portable power. Speaking tubes and mechanical telegraphs existed, but they were limited by physics, by the distance sound could travel through air, or how far a mechanical linkage could extend before friction made it unworkable. Electrical signals could travel much farther, essentially unlimited distance, if you had enough wire and enough intermediate relay points. But each relay needed power, and that power needed to be available wherever the relay was located, regardless of whether there was a generator nearby. Transportation was on the verge of change, though most developments focused on steam engines and internal combustion. Still, experimenters imagined electrical vehicles, motors powered by current rather than exploding fuel. The motor technology existed in crude form, demonstrated the principle that electricity could create rotation, could do mechanical work, but a vehicle needed to carry its power source with it, and no available electrical storage could provide enough sustained current to move significant weight over useful distances. Scientific instruments increasingly depended on electrical phenomena. Researchers wanted to measure tiny currents, detect faint signals, perform experiments that required precise control over electrical input. Generators were too coarse for this work, their output varying with the speed of rotation, affected by mechanical inconsistencies. Static electricity was too unpredictable, too sensitive to humidity and other environmental factors. What was needed was a source of electricity that could be adjusted precisely, that produced consistent output regardless of external conditions, that could be duplicated so that experiments in different locations used identical power sources. The military applications were being considered, though quietly. Electrical detonation of explosives would allow safer, more precise control than fuses burning at uncertain rates. Signaling between positions could happen faster through electrical telegraph than through visual flags or messengers on horseback. Naval vessels could use electrical systems for internal communication, coordinating actions across the length of a ship more efficiently than speaking tubes. But all of these applications required power that could be stored, moved, deployed in locations where running a generator was impractical or impossible. Even illumination for reading at night, simple personal convenience, was constrained by the absence of portable electrical storage. You could read by candlelight or oil lamp, but both required fuel that needed replacing. Both created fumes and heat. Both presented fire risks. An electrical reading light would be cleaner, safer, more convenient. But it required a small, portable source of steady current, something that could sit on a desk or bedside table, providing hours of light without attention, without danger, without the smell of burning oil soaking into curtains and clothing. The need was becoming urgent across multiple domains simultaneously. Inventors, scientists, entrepreneurs, military planners, all wanted the same thing from different angles. They wanted electricity, freed from its generators, made portable, made storable, made reliable. The device that could do this would enable dozens of applications immediately, would make possible things that were currently only imaginable. The economic value would be enormous, the strategic value significant, the scientific value immeasurable. The first working device emerged from observations about frog legs twitching when touched with different metals. A researcher noticed that when two dissimilar metals made contact with muscle tissue simultaneously, the muscle contracted as if shocked. The effect was repeatable, consistent, didn't require any external source, of electricity. The metals and the moist tissue were creating electricity somehow, generating current through chemical interaction rather than mechanical generation or static accumulation. The principle was investigated methodically. Different metal combinations produced different strengths of effect. Certain pairings worked better than others. Zinc and copper showed particularly strong results. Silver and zinc worked well. The presence of moisture was essential. The tissue acting as a conductor and facilitator of whatever chemical process was creating the electrical effect. Dry metals touching each other produce nothing, but introduce any acidic or salty liquid, and current appeared. The configuration was refined through experimentation. Instead of frog legs, which deteriorated quickly and were inconvenient to maintain, researchers used cloth or paper soaked in brine or dilute acid. Discs of metal were cut to uniform size, stacked in alternating pattern. Copper disc, acidified cloth, zinc disc, copper disc, acidified cloth, zinc disc, repeating upward in a column. Wire attached to the top and bottom of this stack carried current, weak but measurable, steady as long as the moisture remained. The voltage increased with height. More discs meant more current, the electrical pressure building as chemical reactions occurred at each layer, each junction between dissimilar metals, contributing its small portion to the total. You could build a stack as tall as was practical, limited only by the mechanical stability of the tower and the weight of accumulated metal. Some experimental versions stood several feet high, dozens of cell pairs generating enough voltage to produce noticeable shocks, to create small sparks, to decompose water into its component gases. The device was messy, temperamental, required constant maintenance. The acidic liquid evaporated, needed replenishing. The cloths dried out, had to be moistened again. Metal surfaces corroded, became coated with reaction products that reduced efficiency. The zinc discs gradually dissolved, consumed by the chemical process that generated the current, needing replacement after extended use. But despite these limitations, the device worked, produced electricity without any external input beyond the gradual consumption of zinc. The implications were recognized immediately, even if the full theory wasn't understood. Here was electricity on demand, no rubbing required, no spinning generator needed. You could sit the device on a table, connect wires whenever you wanted current, disconnect when you were finished. The electricity didn't leak away like charge stored in primitive capacitors. It remained available, waiting in the form of chemical potential energy that converted to electrical energy when a circuit was completed. Early adopters were researchers who needed electricity for experiments. The device was expensive to build, required metals that weren't cheap, needed attention and maintenance that made it unsuitable for casual use. But for someone conducting electrical studies, for someone trying to understand the relationship between current and magnetism, between voltage and chemical decomposition, this was invaluable. Reproducible results required reproducible power sources, and the stack provided that in ways generators and static electricity never could. The first practical applications were demonstrations and education. Universities acquired these devices, used them to teach students about electrical phenomena. Public lectures featured the stack prominently, showing audiences how this arrangement of common materials could create the mysterious force called electricity. The visible construction helped demystify the process, made electricity seem less like magic and more like chemistry, something that followed rules that could be understood and predicted and controlled. Improvements came through understanding the chemistry better. The acidified liquid was acting as an electrolyte, allowing ions to move between the metal plates, completing the chemical reaction that generated current. Different acids produced different results. Sulfuric acid diluted in water worked well, but was dangerous to handle, corroded anything it touched. Salt water was safer, but less efficient. Researchers experimented with various formulations, seeking the optimal balance between performance and practicality. The configuration evolved from vertical stacks to other arrangements. Some designers created horizontal layouts, plates suspended in containers of liquid rather than stacked dry. This kept the electrolyte from evaporating as quickly, made it easier to replenish when needed. The containers could be glass jars, ceramic vessels, anything that resisted acid corrosion. Multiple jars could be connected in series, their voltages adding together, or in parallel, their currents combining while voltage remained constant. The problem of zinc consumption remained fundamental. The metal was being oxidized, dissolving into the electrolyte, its atoms giving up electrons that flowed through the external circuit. This was the source of the electrical energy, the chemical potential difference between zinc and copper being converted into electron flow. But it meant the zinc was fuel, consumed like coal in a steam engine, needing replacement as it was used up. The device was not truly storing energy. It was converting stored chemical energy into electrical energy on demand. Hydrogen gas bubbled off the copper plates during operation, a byproduct of the reactions occurring there. The bubbles accumulated on the metal surface, creating an insulating layer that reduced the efficiency of the device. This polarization effect meant that the output voltage dropped over time during use, recovered partially when the device was allowed to rest. Users learned to work around this, operating intermittently, giving the gas bubbles time to dissipate between periods of current draw. Different applications demanded different configurations. Telegraph systems needed consistent voltage over long periods, prioritized stability over maximum current. Experimental apparatus for electroplating needed high current, could tolerate voltage variations. Medical devices required careful control, the ability to adjust output to safe levels. No single design served all purposes well, so variations proliferated, each optimized for particular uses, each with trade-offs between different performance characteristics. The expense of building these devices limited their adoption. Copper and zinc were not precious metals, but they weren't cheap either, especially in the quantities needed for for powerful versions. The assets required careful handling, added ongoing cost and complexity. Only institutions and wealthy individuals could afford to own and operate these systems. The average person had no access to portable electricity, continued to depend on candles and oil lamps, on mechanical devices, on all the limitations that had always constrained daily life. But the principle had been established, proven functional even if not yet refined. Chemical reactions could generate electricity, could do so steadily and reliably, could be packaged into relatively compact devices that required no external power source. The path forward was visible even if the details remained unclear. Better materials, better electrolytes, better configurations would come. The fundamental concept was sound, waiting only for incremental improvements to make it practical for broader use. Researchers began investigating other metal combinations, seeking pairs that would produce higher voltages, last longer, avoid some of the problems that plagued the zinc-copper arrangement. Iron and copper were tried, lead and copper, various alloys with different compositions. Each combination had its own characteristics, its own advantages and drawbacks. The search for the ideal pairing would continue for decades, each small improvement adding to the collective knowledge, bringing the technology slowly closer to widespread usefulness. The telegraph demanded better power sources and drove their development. Early telegraph lines used the existing chemical cells, strings of jars connected together to provide enough voltage to send signals over miles of wire. But the inconsistency was problematic. Voltage would drop during transmission of long messages, making the received signal weak and difficult to read. The operator would need to pause, let the system recover, then continue. Communication was possible, but inefficient, frustrating, unreliable enough to limit the technology's usefulness. New cell designs emerged specifically for telegraph use. Larger plates provided more surface area for reactions, increased the available current. Better electrolyte formulations reduced internal resistance, allowed more of the generated voltage to reach the external circuit instead of being lost to internal losses. Sealed containers prevented evaporation, extended the time between maintenance. The improvements were incremental, but meaningful. Each generation of cells lasting longer, requiring less attention, providing steadier output than the previous version. The gravitational cell arranged different liquids in layers, exploiting their different densities to keep them separated. Copper sulfate solution, dense and blue, settled at the bottom. Zinc sulfate solution, lighter and clear, floated above it. The copper electrode sat in the bottom layer, the zinc electrode in the top layer. The two solutions slowly intermixed through diffusion, but the process was gradual enough that the cell could operate for weeks before needing fresh electrolyte. The current was steady, the voltage reliable, the maintenance minimal compared to earlier designs. Telegraph offices accumulated dozens of these cells, racks of glass containers filled with colored liquids, connected by networks of copper wire. The The smell of sulfuric acid was constant, a sharp chemical odor that permeated the workspace. The cells required monitoring, checking levels, occasionally pouring off spent solution and adding fresh electrolyte. But the maintenance had become routine, manageable, no longer requiring constant attention from skilled technicians. Telegraph operators could focus on sending and receiving messages rather than nursing temperamental power sources. The cells were heavy, filled with liquid and metal, each one weighing several pounds. Moving them required care, the glass fragile, the liquid corrosive if spilled. Installations became permanent fixtures, rooms dedicated to housing the electrical supply for the telegraph equipment. Ventilation was important, the chemical reactions producing fumes that needed to be exhausted. Temperature control mattered too, the cells performing differently when cold or hot, requiring relatively stable environmental conditions for consistent output. Railroads adopted the telegraph eagerly, using it to coordinate train movements, to prevent collisions, to communicate schedules across their networks. Each station needed electrical power for the telegraph equipment, which meant each station needed cells, needed someone responsible for maintaining them, needed a supply of replacement materials. The logistics of keeping hundreds of telegraph stations powered was significant, but the value of instant communication over distance justified the effort and expense. The diversity of cell designs increased as different users had different needs. Some applications required high current for brief periods. Others needed low current sustained for hours. Some operated in cold environments, others in heat. Cells were developed with different electrolytes, different electrode materials, different configurations, each optimized for particular conditions. There was no universal design, no single best solution, just a growing catalog of options from which users could select based on their specific requirements. The manufacturing of cells became a specialized industry. Small workshops produced them in batches, selling to telegraph companies, to research institutions, to anyone who needed portable electrical power. The quality varied considerably, some manufacturers producing reliable products, while others cut corners, used inferior materials, delivered cells that failed prematurely. Buyers learned to be selective, to test samples before ordering quantities, to build relationships with suppliers who consistently delivered functional equipment. The medical profession began using electrical current more systematically, and this required reliable, controllable power sources. Early electrical therapy devices had used hand-crank generators, induction coils that produced irregular pulses when a handle was turned. The effect was crude, difficult to calibrate, impossible to reproduce precisely. Cells offered steady current that could be measured, adjusted with precision, applied to patients with some confidence in consistency from one treatment to the next. Medical cells were typically smaller than telegraph installations, designed to be portable enough to move between rooms, between buildings, occasionally transported to patients' homes for treatment. The containers were robust, often ceramic or thick glass, protected in wooden cases with handles. The voltage needed to be adjustable, so multiple cells could be connected or disconnected easily, or tapped at different points to provide varying levels of electrical stimulation. Safety was paramount. The current kept low enough to avoid harm even if applied incorrectly. Batteries of cells, multiple units connected together, became common in hospitals and clinics. The term battery had originally meant an artillery battery, multiple guns arranged together for combined effect. The electrical meaning borrowed this sense, multiple cells working together to provide more power than any single unit could deliver alone. A battery might contain 6 cells, 12, 24, depending on the application. The cells sat in racks, labeled and numbered, their state of charge tracked in logbooks. The tracking was necessary because cells degraded with use, their performance declining as the zinc was consumed. As the electrolyte became contaminated with reaction products, as the electrodes accumulated coatings that reduced efficiency, a cell that had been in service for months produced less voltage than a fresh cell, drew down faster under load, recovered more slowly when allowed to rest. Operators learned to recognize the signs of aging cells, to rotate them out of service before they failed completely, to maintain spare capacity so that a dying cell could be replaced without interrupting operations. Disposal became a problem as cell use increased. The spent electrolyte was acidic, toxic, couldn't simply be poured onto the ground without contaminating soil and water. The corroded zinc and copper had some salvage value, but required processing to reclaim. Urban areas began to see accumulations of dead cells discarded behind telegraph offices, in hospital basements, anywhere operators needed to clear space for fresh units. The early environmental impacts of electrical technology were already appearing, small in scale, but foreshadowing larger issues that would emerge as adoption spread. Portable cells started to appear for personal use, though they were expensive luxuries. A wealthy individual might own a small battery for powering a doorbell, for electrical experiments as a hobby, for charging medical devices. These units were compact versions of larger industrial cells, sometimes single jars that could be carried in a case, sometimes small batteries of 2 or 3 cells wired together. The market was limited, the devices more curiosity than necessity, but they demonstrated that electrical power could be domesticated, brought into homes, made available for individual use rather than only institutional applications. The standardization of voltage became important as more devices were designed to run on electrical power. Telegraph equipment expected a certain voltage range, medical devices another, experimental apparatus yet another. Cell manufacturers began labeling their products with nominal voltage, allowing buyers to select appropriate units for their needs. But the actual voltage varied with temperature, with age, with current draw, so the labeled value was approximate, a guideline rather than a precise specification. Devices needed to tolerate some variation, to function across a range of supply voltages rather than requiring exact values. Research into improving cell chemistry accelerated, driven by commercial demand and scientific curiosity. Universities established laboratories dedicated to studying electrochemistry, investigating the fundamental processes that generated current in cells, seeking better understanding that could guide development of improved designs. The work was painstaking, involving careful measurement of tiny voltage differences, precise analysis of electrolyte composition, systematic testing of different material combinations under controlled conditions. Progress was incremental, measured in small percentages of improvement rather than dramatic breakthroughs, but the accumulated knowledge grew steadily, enabling each generation of cells to outperform the previous. The chemistry happening inside cells was becoming better understood through careful experimentation and theoretical work. At the zinc electrode, zinc atoms were giving up electrons, becoming zinc ions that dissolved into the electrolyte. These freed electrons flowed through the external circuit, doing useful work, eventually arriving at the copper electrode. There, other chemical reactions consumed the electrons, completing the circuit. The process was oxidation reduction, one material losing electrons while another gained them, the electron flow between these two processes constituting the electrical current. The electrolyte's role was to allow ionic current inside the cell while preventing direct contact between the electrodes. If zinc and copper touched directly, the reaction would still occur, but the electrons would flow through the point of contact rather than through the external circuit, generating heat at the junction rather than powering anything useful. The electrolyte kept the metals separated while providing a path for ion movement, creating a controlled environment where chemical potential energy converted efficiently into electrical energy. The surface area of the electrodes determined how much current the cell could deliver. A small electrode could only support a limited reaction rate. The chemical processes occurring at the metal electrolyte interface being limited by available surface. Larger electrodes allowed faster reactions, higher current output, though they also required more material, more electrolyte, larger containers. Cell designers balanced these factors, sizing electrodes appropriately for intended applications, neither oversizing and wasting material, nor undersizing and limiting performance. The spacing between electrodes affected internal resistance. Closer spacing meant ions had shorter distances to travel through the electrolyte, reducing resistance, allowing more current to flow for a given voltage. But closer spacing also increased the risk of short circuits, of deposits building up between electrodes, of manufacturing defects creating unintended contact points. The optimal spacing was a compromise, close enough for efficient operation, but far enough for reliability and safety. Temperature influenced cell performance significantly. Chemical reactions proceeded faster at higher temperatures, potentially increasing current output, but also accelerating degradation. Cold temperatures slowed reactions, reduced available current, could even freeze liquid electrolytes in extreme conditions. Cells designed for outdoor use in winter needed formulations that remained liquid at low temperatures, often involving salts that depressed the freezing point, though these sometimes reduced overall performance compared to formulations optimized for room temperature operation. The voltage of a single cell was determined by the chemical potential difference between the electrode materials, typically between 1 and 2 volts, depending on the specific metals and electrolytes used. This was a fundamental limit, couldn't be exceeded by making the cell larger or using more electrolyte. To achieve higher voltages, multiple cells had to be connected in series, each one adding its voltage to the total. A 12-volt battery required at least 8 cells in series, more if each cell produced less than the theoretical maximum due to internal resistance and other losses. The capacity of a cell, how long it could deliver current before being exhausted, depended on the quantity of reactive material available. More zinc meant more material could be oxidized before the cell was depleted. Larger volume of electrolyte meant the reaction products could accumulate longer before concentrations became limiting. Capacity was measured in various units, sometimes by weight of zinc consumed per hour of operation, sometimes by the total charge that could be delivered before voltage dropped below useful levels. Different measurement schemes made comparing cells from different manufacturers difficult. The shelf life of cells became important for applications requiring long-term storage. Some cell chemistries degraded even when not in use, the electrodes slowly corroding in the electrolyte, the reactive materials gradually being consumed by parasitic reactions. Other designs were more stable, could sit for months or even years and still function when needed, though perhaps at slightly reduced capacity. Cells for emergency use, for backup power, for infrequent applications needed good shelf life, even if other performance characteristics were less optimal. Rechargeable cells emerged when researchers discovered that certain chemical reactions could be reversed by passing current backward through the cell. Lead plates in sulfuric acid underwent chemical changes during discharge, both plates becoming coated with lead sulfate. But applying external voltage reversed these changes, converting the lead sulfate back to the original materials, restoring the cell to a charged state. The device could be used, exhausted, recharged, used again, repeating this cycle many times before the plates deteriorated beyond function. The lead-acid cell became the dominant rechargeable design despite several limitations. The sulfuric acid was dangerous, highly corrosive, produced toxic fumes during charging. The lead plates were heavy, making the cells massive for their electrical capacity. But the chemistry was robust, tolerant of rough handling, capable of delivering high currents when needed. The cells were relatively inexpensive to manufacture, the materials common and easily obtained. For stationary applications where weight didn't matter and the hazards could be managed, lead-acid cells were practical and economical. Charging required a separate power source, typically a generator driven by steam engine, water wheel, or later by internal combustion engine. The generator produced voltage higher than the cell's nominal voltage, forcing current backward through the cell, driving the chemical reactions in reverse. The charging rate had to be controlled carefully. Too fast, and the cells overheated, produced dangerous amounts of hydrogen gas, could even crack from thermal stress. Too slow, and the charging took many hours, tying up equipment and space. Operators learned the optimal rates through experience, developed procedures that balanced speed against safety. The charged cell sat heavy with potential energy, the chemical configuration unstable, eager to revert to the discharged state. This stored energy was accessible immediately. No warm-up period required, no mechanical starting procedure. Connector load and current flowed instantly, continuing steadily until the reactive materials were depleted or the load was removed. This instant availability made rechargeable cells ideal for applications requiring power on demand, for backup systems that might sit idle for long periods, but needed to activate immediately when called upon. Battery rooms in industrial facilities housed racks of these cells, entire walls covered with glass-cased lead plates immersed in acid. The rooms required ventilation to exhaust hydrogen produced during charging, required drainage in case of acid spills, required access for maintenance since the cells needed regular attention. Water evaporated from the electrolyte during operation, and especially during charging, needing periodic replacement with distilled water to maintain proper electrolyte levels. The plates accumulated deposits, required occasional cleaning, occasional replacement as they wore out. The cycle life of rechargeable cells was limited, degrading gradually with each discharge and recharge. The lead plates slowly changed structure, active material flaking off, sulfation becoming irreversible, internal resistance increasing. After hundreds of cycles, sometimes thousands for well-maintained cells, performance declined to the point where replacement was necessary. The dead cells were valuable for their lead content, could be processed to reclaim the metal for manufacturing new cells, creating a recycling loop before recycling became a common concept. Different charging strategies affected longevity and performance. Slow charging at low current was gentlest on the cells, minimized heat and gas production, allowed the chemical reactions to proceed more completely. Fast charging at high current was convenient but more stressful, created temperature gradients within the cells, sometimes left portions inadequately charged. Trickle charging, maintaining a constant low current to compensate for self-discharge, kept cells ready for use, but also kept them warm, gassing slightly, requiring more frequent water additions. The development of portable rechargeable cells opened new possibilities. A cell could be charged overnight when power was available, then disconnected and carried to a location without generators or grid power. The stored energy went along, available for use wherever needed. This enabled portable lighting for mine workers, for inspectors working in dark spaces, for emergency crews responding to situations where bringing a generator was impractical. The weight was significant, the capacity limited, but the convenience of having power available anywhere was valuable enough to justify the limitations. The electrical grid changed everything about how power was distributed, but it created new demands for batteries. Early electrical systems were direct current, power stations generating at fixed voltage, transmitting through copper wires to customers within a limited radius. The transmission losses were substantial, voltage dropping with distance, limiting how far electricity could travel economically. Batteries at customer locations could supplement the grid supply, providing power during peak demand periods, compensating for voltage fluctuations, ensuring consistent power for sensitive equipment. The standardization of voltage levels became necessary as more devices were designed to operate on electrical power. Some equipment expected 100 volts, others needed 12, still others required 200. Batteries were manufactured in standard configurations to match these common voltages. A 12-volt battery contained 6 2-volt cells in series. A 6-volt battery contained 3 cells. The cells themselves became more uniform, manufactured to specifications that ensured predictable performance, interchangeability between units from different production batches. Dry cells eliminated the liquid electrolyte problem that had plagued earlier designs. The electrolyte was absorbed into paste or powder, immobilized so it couldn't spill even if the cell was inverted. The entire assembly was sealed into a metal can, making it robust enough for rough handling, portable enough for casual use. These cells couldn't be recharged economically, were designed to be used once and discarded, but they were convenient in ways that liquid cells could never match. No maintenance, no checking levels, no corrosive spills. The carbon-zinc chemistry became the standard for dry cells. A zinc can serve as both container and negative electrode, the anode being consumed during discharge. Inside, a carbon rod formed the positive electrode, surrounded by a mixture of carbon powder, manganese dioxide, and electrolyte paste. The chemistry was well understood, reliable, inexpensive to manufacture. The cells produced about 1.5 volts when fresh, declining gradually as they discharged, eventually dropping below 1 volt when most of the reactive material was consumed. Sizes became standardized, enabling device manufacturers to design equipment knowing that replacement cells would be available in specific dimensions. The cylindrical format dominated, various diameters and lengths designated by letters and numbers. Larger cells had more capacity, could deliver current for longer periods before exhaustion. Smaller cells were more portable, fit into compact devices, though they exhausted more quickly. The standardization created a market where batteries were interchangeable commodities, no longer requiring matching to specific equipment from specific manufacturers. Flashlights became ubiquitous with the availability of reliable dry cells. A simple device, just a case holding batteries in series to achieve the necessary voltage, a small incandescent bulb, a switch to complete the circuit. The filament glowed when current flowed, producing light without flame, without heat buildup that made the device too hot to hold, without consuming oxygen from enclosed spaces. Miners carried them, police officers, anyone who needed portable light. The batteries lasted hours on a single set, were cheap enough that replacement was economical when they failed. portable radios emerged as battery technology improved, though they required relatively high voltage and consumed power quickly. Multiple dry cells stacked together provided the 90 or 120 volts needed for vacuum tube operation. The batteries were large, heavy, expensive to replace, but the ability to receive radio broadcasts anywhere, independent of electrical outlets, was compelling enough to justify the cost and inconvenience. Remote locations, ships at sea, military units in the field, all used battery-powered radios for communication and entertainment. The disposable nature of dry cells created waste streams that grew with adoption. Spent cells contained zinc, manganese, carbon, various chemicals, all mixed together in a corroded mass. They accumulated in trash heaps, in landfills, their contents slowly leaching into soil. The scale was small initially, the environmental impact negligible, but the trend was concerning to anyone thinking about long-term consequences. Each incremental improvement in battery technology, each new application, each price reduction that made batteries accessible to more users added to the accumulating waste. Hearing aids became practical with small battery cells, devices that could fit in pockets or behind ears, restoring partial hearing to people who had been isolated by deafness. The batteries were small buttons, zinc-air chemistry providing good energy density in miniature form. Air entered through small holes in the case, participated in the chemical reaction, allowed high capacity relative to the cell's size. The batteries lasted days or weeks depending on usage, were inexpensive enough that replacement was affordable even for users of modest means. Wristwatches transitioned from mechanical springs to battery power, electronic circuits replacing gears and escapements. The batteries were tiny, button cells that fit within watch cases, lasting a year or more before needing replacement. The watches kept better time than mechanical equivalents, required less maintenance, tolerated rough treatment that would damage delicate mechanical movements. The battery was sealed inside during manufacture, not user replaceable in early models. The entire watch sometimes discarded when the battery died, though later designs allowed access for replacement. Cameras adopted battery power for light meters, for motorized film advance, for electronic shutters. The convenience of automation required electrical power, and batteries made that power portable. Photographers carried spare batteries, changed them between the mechanical and battery-powered functions when cells were exhausted. The power demands were modest, button cells or small cylindrical cells adequate for most applications, lasting through many rolls of film before needing replacement. Calculators shifted from mechanical to electronic, the transition enabled by both semiconductor technology and improved batteries. Early electronic calculators were desktop units powered by outlets, but miniaturization allowed pocket-sized devices running on small batteries. The computational capability was limited by modern standards, but revolutionary compared to mechanical calculators or slide rules. Students, engineers, accountants, anyone who worked with numbers regularly adopted these devices eagerly, despite the need for periodic battery replacement. Medical devices became increasingly battery-dependent. Portable diagnostic equipment allowed doctors to make house calls with sophisticated instruments. Hearing aids improved the quality of life for millions. Pacemakers, implanted surgically, used sealed batteries to regulate heartbeats for years before requiring replacement. The batteries for implantable devices needed special characteristics: absolutely reliable, long-lasting, biocompatible, small enough to fit in the device, but energetic enough to function for years. The development of these specialized cells required extensive research, careful quality control, rigorous testing before deployment in life-critical applications. Toys increasingly contained batteries, motors, and lights, and sound generators, powered by cells that fit into compartments in plastic housings. Children's toys that moved on their own, that made noise, that lit up, all required batteries. Parents bought them in packages, kept supplies available, dealt with the frustration of devices going silent at inconvenient moments when batteries died. The toy industry became a significant consumer of batteries. Millions of cells sold annually for devices that provided entertainment rather than essential function. The environmental cost of battery production and disposal was growing, but largely ignored. Mining operations extracted zinc, manganese, lithium, other materials from the earth in increasing quantities. Processing plants refined these materials, consuming energy, producing waste. Manufacturing facilities assembled cells by the millions, their output growing annually as more devices adopted battery power. The spent cells accumulated, their chemical contents eventually breaking down, releasing metals and compounds into the environment. Recycling infrastructure was minimal, economic incentives insufficient to make recovery profitable at the existing small scale. Battery quality varied considerably between manufacturers and price points. Cheap cells used lower-grade materials, less precise manufacturing, provided adequate performance initially, but degraded quickly, sometimes leaked corrosive materials before being fully discharged. Premium cells cost more but lasted longer, performed more consistently, were less likely to fail catastrophically. Consumers learned to judge quality by brand reputation, by price, by experience with previous purchases. The market segmented into budget options for non-critical applications and reliable options for important devices where failure was unacceptable. Portable electronics began their exponential growth, each new device category creating demand for batteries tailored to specific requirements. Portable cassette players needed cells that could deliver steady current for hours, preferably in compact form that fit alongside the tape mechanism and playback electronics. The devices were popular among younger users, carried in pockets and bags, used while commuting, while exercising during leisure time. Battery life became a key specification. Manufacturers competing on how many hours of playback a single set of cells could provide. Rechargeable cells for consumer applications improved dramatically. Nickel-cadmium chemistry offered rechargeability in standard sizes, cells that looked identical to disposable dry cells but could be recharged hundreds of times. The initial cost was higher, but the lifetime economics favored rechargeables for high-use applications. Chargers became common household items, simple devices that applied controlled current to cells overnight, ready for use the next day. The cadmium was toxic, created disposal concerns, but the convenience and cost savings drove adoption despite environmental questions. The memory effect in nickel-cadmium cells was a practical limitation that required user education. If the cells were repeatedly recharged before being fully discharged, they seemed to remember the partial discharge depth, subsequently providing only that amount of capacity even when discharged more deeply. The effect was reversible through deep discharge-recharge conditioning cycles, but many users didn't understand this, concluded that rechargeable cells were unreliable, reverted to disposables. Manufacturers tried to educate users, included instructions about proper charging procedures, but misconceptions persisted. Power tools transitioned from corded to cordless. The freedom from power cords enabled by battery packs containing multiple cells. The tools required high current, substantial power to drive motors under load. Battery packs were heavy, their weight noticeable when holding tools overhead or using them for extended periods. But the convenience of working anywhere without extension cords, without generators, without planning around outlet locations, justified the weight and the limitation of finite runtime before recharging. Professional tradespeople adopted cordless tools despite their limitations, gradually refined their work habits around battery capacity and charging schedules. Laptop computers emerged, portable machines that could operate disconnected from wall power for hours. The battery packs were substantial, containing many cells wired together to provide both the necessary voltage and adequate capacity for meaningful runtime. Battery life became a primary specification, manufacturers competing on how long machines could run between charges. Users learned to manage power consumption, adjusting screen brightness, spinning down hard drives, choosing between performance and battery life, depending on whether they were plugged in or running on battery. Cell phone batteries required careful optimization. The devices needed to remain on continuously, waiting for calls, but had to conserve power to provide days of standby time. Active use, actually making calls, consumed much more power, draining batteries in hours of talk time. The batteries were rechargeable, designed to fit the specific form factor of each phone model, shaped to use available space efficiently. Users developed habits of nightly charging, keeping phones tethered to chargers overnight, ensuring full charge for the next day's use. The proliferation of battery-powered devices created problems with charger compatibility. Each device often required its own specific charger, using different voltage, different current, different connector types. Households accumulated drawers full of chargers, often orphaned when the original device was replaced or discarded. The lack of standardization was economically inefficient, environmentally wasteful, frustrating for users who needed to carry multiple chargers when traveling. Some standardization efforts emerged, but adoption was slow. Manufacturers resistant to losing the accessory revenue that proprietary chargers provided. Battery anxiety became a recognized phenomenon. The stress of monitoring remaining charge, worrying about devices dying at critical moments, planning activities around charging opportunities. People checked battery indicators compulsively, carried spare batteries or portable chargers, modified behavior to conserve power when running low. The dependence on battery-powered devices created vulnerability. The functionality of essential tools contingent on maintaining adequate charge levels. Power outlets in public spaces became valued resources, seats near them preferred. Etiquette around sharing access developing informally. Lithium chemistry brought significant improvements in energy density, capacity per unit weight, and volume, substantially better than earlier rechargeable technologies. Lithium ions move between electrodes during charging and discharging, intercalating into the crystal structures of the electrode materials without consuming the electrodes themselves as earlier chemistries had. This allowed many more charge-discharge cycles before degradation, hundreds or thousands, depending on usage patterns and care. The higher voltage of lithium cells, typically 3.6 or 3.7 volts per cell, meant fewer cells needed to achieve desired pack voltages. The lithium cells were sensitive to overcharging, over-discharging, and physical damage. Exceeding voltage limits during charging could cause thermal runaway, the cell heating uncontrollably, potentially catching fire or exploding. Deep discharge damaged the cell chemistry, sometimes irreversibly. Physical puncture or crushing could create internal short circuits with similar catastrophic results. These characteristics required protective circuitry in every battery pack, monitoring cell voltages, limiting current, disconnecting cells when parameters exceeded safe ranges. The added complexity increased cost, but was essential for safety. Battery management systems became sophisticated, microcontrollers dedicated to monitoring and controlling battery behavior. The systems tracked charge state, estimated remaining capacity, balanced cells within multi-cell packs to ensure even wear, communicated with device processors to report battery status. The algorithms were complex, accounting for temperature effects, for aging, for the relationship between voltage and actual remaining capacity, which wasn't linear. The accuracy of the fuel gauge, the prediction of how much runtime remained, depended on the quality of these algorithms and the accuracy of their underlying assumptions. Electric vehicles emerged as practical transportation, enabled by lithium battery technology that provided sufficient energy density to achieve useful range. The battery packs were massive, containing thousands of individual cells, weighing hundreds of pounds, occupying significant vehicle volume. The cost of the battery pack represented a large fraction of total vehicle cost, making electric vehicles expensive compared to conventional alternatives despite lower operating costs. Range anxiety mirrored the battery anxiety of portable electronics, but with higher stakes, running out of charge, potentially leaving drivers stranded far from charging infrastructure. Charging infrastructure for electric vehicles required substantial electrical capacity, installations that could deliver tens of kilowatts to recharge large battery packs in reasonable time. Slow charging overnight at home was practical for daily commuting, but longer trips required faster charging, higher power levels, specialized equipment. The infrastructure was sparse initially, concentrated in urban areas and along major highways, creating challenges for adoption, especially in regions with low population density or limited electrical grid capacity. Grid-scale battery storage began to appear. Large installations that could absorb excess electrical generation during low demand periods, discharge during peak demand, helping to balance supply and demand on electrical grids. The battery systems were substantial, often filling entire buildings or fields of containers, containing megawatt hours of stored energy. The economics were marginal, cost per stored energy unit still high compared to other grid balancing methods, but improving steadily. The ability to store renewable energy, to shift solar generation from midday to evening, to capture wind power for later use, was valuable enough to justify deployment even at higher cost than ideal. Battery chemistry research intensified, universities and corporations investing heavily in finding better materials, better configurations, higher energy density, faster charging, longer life, lower cost, improved safety. Solid-state electrolytes promised to eliminate flammability concerns. Silicon anodes could theoretically store much more lithium than conventional graphite. Various cathode materials offered different trade-offs between energy density, power capability, cycle life, and cost. The research was incremental, each improvement measured in single-digit percentages, but the accumulated progress was substantial, each generation of batteries meaningfully better than the previous. The geopolitics of battery materials became significant. Lithium deposits were concentrated in specific regions, refining capacity dominated by certain countries, creating strategic dependencies similar to oil, but with different geographic patterns. The cobalt used in some cathode formulations came primarily from regions with problematic labor practices and political instability. Supply chain security became a concern for nations dependent on imported batteries, spurring domestic production efforts. Research into alternative chemistries that used more common materials, recycling initiatives to recover materials from spent cells. The manufacturing of lithium cells required precision that earlier battery technologies hadn't demanded. The electrode materials were coated onto thin metal foils in layers measured in micrometers, the thickness controlled carefully to ensure consistent performance. Any contamination, any variation in coating uniformity, any defect in the foil could create points of failure, reduce capacity, shorten life, or create safety hazards. Clean rooms housed the coating equipment, air filtered continuously to remove particles, that could compromise the delicate layers being deposited. The electrode sheets were wound or stacked to create the cell structure, separators between layers preventing direct contact while allowing ion transport. The separator material was critical, a porous membrane that needed to be mechanically strong, chemically stable, thermally robust. If the separator failed, if it melted under heat, or punctured during assembly, or degraded during use, the positive and negative electrodes could touch, creating an internal short circuit. The consequences could be immediate and violent. The cell's stored energy discharged rapidly as heat. Eel electrolyte filling happened in controlled environments. The lithium salts dissolved in organic solvents sensitive to moisture and oxygen. Any water contamination would react with the lithium salts, forming compounds that reduced performance, consumed electrolyte, potentially created gases that pressurized the sealed cell. The filling process evacuated air from the cell, replaced it with electrolyte, sealed the container in continuous automated operations that minimized exposure to ambient atmosphere. The sealed cell then underwent formation, carefully controlled initial charging that established the protective layers at electrode surfaces. Quality control involved testing every cell, checking voltage, measuring capacity, performing safety tests on statistical samples. Cells that failed specifications were rejected, sent for disassembly and material recovery. The reject rate varied with manufacturing maturity, new production lines rejecting higher percentages until processes stabilized. Even small defect rates created significant waste at production volumes measured in millions of cells annually. The rejected cells contained valuable materials, but recovering them required processing that was energy intensive and sometimes environmentally challenging. Battery pack assembly combined individual cells into configurations that met device requirements. The cells were spot welded into series parallel arrangements, connections made by ultrasonic or resistance welding of thin metal strips to the cell terminals. The welding required precise control, enough energy to create solid joints, but not so much as to damage cells or create internal shorts. Automated equipment positioned cells, applied welds, tested connections, assembled packs at rates measured in units per minute for high-volume applications. The protective circuitry mounted onto the cell pack, usually a printed circuit board with sensing resistors, switching transistors, protection integrated circuits, sometimes wireless communication capability. The circuit monitored each cell individually in larger packs, ensuring none exceeded safe voltage limits during charging. None dropped too low during discharge. If any parameter exceeded thresholds, the protection circuit disconnected the pack, preventing damage even if the charging equipment malfunctioned or the load exceeded design limits. Thermal management became critical for larger battery packs, the heat generated during charging and discharging needing to be conducted away to prevent excessive temperature rise. Some packs use passive cooling, metal cases and thermal pads conducting heat to external surfaces where natural convection dissipated it. Others incorporated active cooling, fans moving air through the pack, or liquid cooling systems circulating coolant through passages between cells. The thermal design affected pack size, weight, complexity, cost, but was essential for safety and longevity, temperature being one of the primary factors affecting battery life. Testing facilities subjected cells and packs to abuse conditions, deliberately overcharging, over-discharging, short-circuiting, crushing, puncturing, heating, trying to trigger failures under controlled conditions. The goal was understanding failure modes, ensuring protection systems worked correctly, verifying that catastrophic failures were contained even when safety systems failed. Cells that vented hot gases needed to direct those gases safely away from users. Cells that caught fire needed to be isolated to prevent propagation to adjacent cells. The testing was destructive, expensive, essential for confidence in safety. Recycling infrastructure for lithium batteries developed slowly, challenged by the variety of cell chemistries, the mixing of different battery types in waste streams, the low value of recovered materials relative to processing costs. Early recycling focused primarily on recovering cobalt, the most valuable component in some lithium chemistries. The cells were collected, discharged for safety, then processed through pyrometallurgical or hydrometallurgical methods. Pyrometallurgy burned away organic components, recovered metals from the resulting slag. Hydrometallurgy dissolved materials in acids, separated components through chemical processes. The economics favored recycling only when material prices were high or when regulations mandated it. Processing facilities needed to handle hazardous materials safely, manage environmental impacts, maintain expensive equipment. The volume of batteries entering the waste stream was growing, but still relatively small compared to other recycling industries. Investment in recycling capacity was hesitant. Companies uncertain whether future material prices and regulatory requirements would justify the capital expenditure and operating costs. Transportation of spent batteries created regulatory challenges. The cells were classified as hazardous materials, their residual charge representing fire risk, their chemical contents toxic. Shipping required special packaging, labeling, documentation. Costs increased accordingly, making collection from distributed sources economically difficult. Many spent batteries ended up in general waste streams, buried in landfills where their contents would eventually leach into soil and groundwater. The environmental impact was delayed but inevitable, building slowly as annual battery production and disposal volumes grew. Supply chain complexity increased as battery production scaled globally. Raw materials were mined in certain countries, refined in others, manufactured into cell components in still others, assembled into cells in different facilities, integrated into packs elsewhere, installed into final products in yet other locations. Each step added transportation costs, energy consumption, complexity in tracking material origin and quality. Disruptions anywhere in the chain affected production everywhere, as became apparent when natural disasters, political events, or health crises interrupted normal operations. Capacity expansion required massive capital investment. Building a new cell manufacturing facility cost hundreds of millions, sometimes billions. The equipment specialized and expensive. The time from decision to operational production was measured in years, creating challenges in matching capacity to rapidly changing demand. Overcapacity created financial stress, expensive facilities sitting idle. Undercapacity created supply shortages, rising prices, inability to meet market demand. Forecasting future demand accurately was difficult. The markets for battery-powered devices growing rapidly but unpredictably. Vertical integration became a strategy for large manufacturers, controlling multiple steps of the supply chain to ensure supply, to capture more value, to reduce dependence on external suppliers. Some companies invested in mining operations, securing access to raw materials. Others built refining capacity, processing raw materials into battery-grade compounds. Still others integrated forward into pack assembly or even final product manufacturing. The integration required enormous capital, but provided strategic advantages in a rapidly growing, strategically important industry. Research and development consumed significant resources. Companies and universities investigating next-generation chemistries, manufacturing processes, application-specific designs. The research was global, concentrated in regions with strong technical education systems, with government support for advanced technology development, with established electronics or automotive industries. Patents proliferated, companies building intellectual property portfolios, creating barriers to entry for competitors, establishing positions in technologies that might not commercialize for years, but could eventually dominate markets. Standardization efforts attempted to bring order to the proliferation of cell sizes, chemistries, interfaces, charging protocols. Industry groups convened, drafted standards, lobbied for adoption. But the incentives for standardization competed with incentives for differentiation, for proprietary designs that locked customers into specific ecosystems. The tension between interoperability and competitive advantage was never fully resolved, resulting in partial standardization in some areas, while fragmentation persisted in others. Consumers benefited from standardization where it occurred, but suffered from incompatibility where it didn't. The global distribution of battery manufacturing reflected economic development patterns, labor costs, energy prices, regulatory environments. Production concentrated in regions that could offer competitive advantages in these dimensions. Some countries subsidized battery production, viewing it as strategic infrastructure, investing in capacity that might not be economically justified by pure market forces. Others attracted manufacturing through low labor costs, though automation was reducing labor content in cell production, making labor costs less decisive than previously. Energy costs affected production economics significantly. Battery manufacturing consumed substantial electricity for clean rooms, for coating equipment, for formation charging, for climate control. Regions with low electricity costs, especially from renewable sources, could produce cells more economically while also claiming environmental benefits. Some facilities located near renewable generation, specifically to power production with low-carbon electricity, responding to customer demand for sustainably produced batteries, even if the product itself was chemically identical to conventionally produced cells. Technology transfer from research to production was often slower than hoped. Laboratory demonstrations of new chemistries showed promising characteristics: higher energy density, faster charging, improved safety. But scaling from coin cells in a lab to high-volume manufacturing of large-format cells presented numerous challenges. Materials that worked in small quantities might not be available in production volumes. Processes that functioned in controlled research environments might fail in factory conditions. Costs that seemed reasonable for laboratory experiments often proved prohibitive at commercial scale. The workforce requirements evolved as manufacturing automated. Early battery production was labor-intensive, workers manually stacking electrodes, filling cells, testing output. Modern facilities were highly automated, robots handling materials, vision systems inspecting quality, computer-controlled equipment managing processes. The workforce shifted toward maintenance technicians, process engineers, quality specialists, fewer in number, but more highly skilled. The transition created employment disruptions in regions transitioning from old to new manufacturing methods. Environmental regulations varied by region, affecting where certain manufacturing processes located. Regions with strict environmental controls required expensive pollution control equipment, careful waste management, regular monitoring and reporting. Regions with lax enforcement allowed cheaper operation but created environmental damage and worker health risks. Some companies chose higher environmental standards globally, exceeding local requirements, driven by corporate policy or customer expectations. Others optimized for local minimums, creating disparities in environmental impact depending on production location. Trade tensions affected battery supply chains, tariffs imposed on cells or materials, restrictions placed on technology transfer, export controls limiting where certain advanced batteries could be sold. The industry was simultaneously global in its supply chains and fragmented by national interests, creating complicated navigation requirements for companies operating internationally. Some manufacturing was reshored to reduce geopolitical risk, accepting higher costs for supply chain security. Other production moved to neutral countries, avoiding trade restrictions affecting specific bilateral relationships. The developing world experienced battery technology differently. Adoption patterns shaped by infrastructure availability, income levels, local conditions. In regions without reliable electrical grids, batteries became enablers of basic services, storing solar-generated electricity for use after dark, powering communication devices, enabling economic activities previously impossible. In more developed regions, batteries were convenience items, incremental improvements to existing capabilities. The global distribution of benefits from battery technology was uneven, shaped by existing disparities in wealth and infrastructure. Off-grid communities adopted battery storage eagerly, the technology enabling modern amenities without requiring grid connection. Solar panels generated electricity during daylight, charging battery banks that provided power after sunset. The systems were modular, scalable from single households to entire villages, sized according to energy needs and available budget. The batteries were typically lead-acid for cost reasons, though lithium systems appeared where higher cost could be justified by longer life and better performance. Medical refrigeration in remote areas depended on battery-backed solar systems, vaccines, and medications stored safely where grid power was unavailable or unreliable. The refrigerators ran continuously, critical loads that couldn't tolerate power interruptions. Battery capacity was sized generously, providing days of operation during cloudy periods, ensuring medications remained viable regardless of weather. The cost of the battery system was substantial, but far less than the cost of spoiled medications or preventable disease from inadequate vaccine storage. Communication infrastructure in underserved regions relied on battery backup, cell towers, and radio repeaters maintaining service during grid outages. The batteries provided hours or days of runtime, depending on capacity and load, bridging gaps until grid power returned or backup generators could be dispatched. The reliability of communication was sometimes life-saving. Emergency calls connecting despite infrastructure challenges, information flowing even when other systems failed. The batteries were often the difference between connected and isolated communities. Agricultural applications in developing regions use batteries for water pumping, irrigation systems operating on solar power, with battery storage allowing pumping during evening hours. The systems enabled farming in areas without grid power, improved agricultural productivity, increased food security. The batteries needed to withstand harsh conditions, temperature extremes, dust, limited maintenance capability. Lead-acid cells were common for their robustness and tolerance of rough treatment, though their weight and maintenance requirements were disadvantageous. Educational technology reached remote schools through battery-powered devices, tablets and laptops, providing access to digital learning resources where grid power was absent or intermittent. The devices charged during school hours when solar panels generated power, battery capacity sufficient for use into evening for homework and study. The technology helped bridge educational gaps, providing students in remote areas access to resources and opportunities previously available only in urban centers, though disparities remain significant. Environmental monitoring equipment in remote locations operated on battery power. Weather stations and pollution sensors and wildlife tracking devices collecting data continuously. The batteries were recharged by solar panels, sized for operation through extended cloudy periods, managing power carefully to maintain operation year-round. The data collected informed environmental policy, tracked climate changes, supported conservation efforts. The battery systems enabling observation in places where grid power would never reach economically. Disaster relief operations deployed battery systems rapidly, providing power for communications, medical equipment, lighting in areas where infrastructure had failed. The batteries were portable, could be transported by helicopter or carried by personnel, set up quickly to restore basic services. Solar panels charged the batteries during day, providing sustainable power without fuel supply logistics. The systems were designed for rapid deployment, rugged enough to withstand rough handling, simple enough for operation by personnel without specialized training. The global battery industry created complex dependencies, regions consuming batteries manufactured elsewhere from materials mined in distant locations. The dependencies were economic but also strategic. Access to batteries affecting national capabilities in communication, transportation, energy storage, defense. Countries without domestic battery production were vulnerable to supply disruptions, to price fluctuations, to potential export restrictions during conflicts or trade disputes. The dependencies motivated some nations to develop domestic capacity despite economic disadvantages, treating battery production as strategic infrastructure worth subsidizing for security reasons. The question of what batteries represented beyond their technical function became increasingly relevant as dependence deepened. They were storage devices in the literal sense, containers for electrical energy, but they also stored human capability, potential action waiting to be released. A charged battery was latent possibility, the capacity to communicate, to illuminate, to transport, to compute, all held in chemical suspension until needed. The philosophy of stored energy was ancient, grain silos and water reservoirs serving similar functions. But electrical storage was different in its immediacy, its versatility, its disconnection from physical bulk. The temporal dimension of batteries changed how people related to energy. Electricity had been immediate, simultaneous with generation, constrained by the synchronous relationship between production and consumption. Batteries broke this temporal coupling, allowed energy to be harvested at one time and used at another, shifted consumption patterns away from generation patterns. This temporal shifting had profound implications for renewable energy, for grid management, for personal autonomy from infrastructure. The battery was a time machine for energy, moving it forward through hours or days or months. The concept of energy independence took concrete form through batteries. An individual with sufficient battery capacity and renewable generation could disconnect from the grid entirely, become self-sufficient in electricity. The reality was more complex, the investment substantial, the maintenance non-trivial, the reliability dependent on weather and geography. But the possibility existed in ways it hadn't before. the technical capability to generate and store enough energy to meet household needs without external supply. The philosophical implications of energy independence paralleled food self-sufficiency or water independence, fundamental resources made autonomous. The relationship between capacity and freedom was direct. More battery capacity meant more freedom from charging infrastructure, from outlets, from scheduling around power availability. But capacity had costs in weight, in volume, in expense, creating trade-offs that shaped behavior and limited freedom in other dimensions. The person carrying a large battery pack for extended runtime traded portability for endurance accepted physical burden for electrical freedom. These trade-offs were individual, varying by use case and personal priority, but they shaped how battery-powered devices were used and valued. The anxiety around depleting batteries reflected deeper concerns about dependence and vulnerability. The battery indicator showing low charge triggered stress responses, prompted behavior changes, created urgency around finding power sources. This wasn't merely inconvenience, it was recognition of dependence, acknowledgement that essential capabilities were contingent on maintaining charge. The anxiety increased with the importance of the device, mild for entertainment devices, but acute for communication devices or medical equipment. The emotional response to low battery warnings revealed how thoroughly batteries had become integrated into basic functioning. The disposal problem raised ethical questions about temporal externalities, present convenience, creating future environmental burden. Each battery used provided benefit to its owner, but created waste that would persist long after the benefit was consumed. The person using the battery rarely dealt with the consequences of its disposal, that burden falling on future populations, on ecosystems, on workers in recycling facilities or communities near landfills. The separation of benefit from consequence was common in industrial systems, but particularly stark with batteries. The immediate utility so visible, while the long-term costs remained abstract and distant. The global inequality in battery access mirrored other resource inequalities, but with specific characteristics. Batteries were not naturally occurring resources like water or arable land. They were manufactured goods requiring complex industrial infrastructure. Access depended on purchasing power, on supply chains, on functioning markets. Regions without access to batteries were excluded from battery-enabled capabilities, creating a form of technological poverty that compounded other disadvantages. The inequality was in capability rather than consumption. The absence of batteries limiting what people could do rather than merely what they could have. The strategic importance of battery technology created national security considerations that shaped research priorities and industrial policy. Countries recognized that battery capability was foundational for military applications, for economic competitiveness, for energy security. The recognition led to subsidies for domestic production, to restrictions on technology transfer, to research programs focused on strategic advancement rather than commercial optimization. The batteries became geopolitical assets, their possession and production capability affecting national power and international relationships. The learning curve of battery technology, the gradual improvement in performance and cost over decades, demonstrated the cumulative nature of technological progress. Each generation of batteries was marginally better than the previous, the improvements small enough that individual steps seemed incremental, but large enough that accumulated progress was substantial. The trajectory suggested that future batteries would continue improving, that limitations that seemed fundamental might eventually yield to better understanding and better engineering. But the trajectory also showed that progress was work-intensive, requiring sustained investment and research, not inevitable, but contingent on continued effort. The standardization of battery formats created network effects, the value of a standard increasing with adoption. A widely used battery size attracted manufacturers, created competition that lowered prices, ensured availability that made devices using that size more practical. But standardization also created lock-in, made it difficult to abandon established formats even when better alternatives existed, because the infrastructure and installed base of devices depended on the standard. The tension between innovation and compatibility was ongoing, new formats competing against established ones, sometimes succeeding through superior performance, but often failing despite technical advantages. The role of batteries in enabling renewable energy deployment was circular and mutually reinforcing. Better batteries made renewable energy more practical by storing intermittent generation. Increased renewable deployment created demand for more battery storage, driving investment and innovation that improved batteries. The positive feedback loop accelerated both technologies, each making the other more valuable. But the loop also created dependencies, renewable energy grids becoming vulnerable to battery supply constraints, battery economics dependent on renewable deployment continuing. The metaphorical usage of battery terminology revealed how deeply the technology had penetrated cultural consciousness. People spoke of recharging themselves, of running low on energy, of needing to plug in and restore capacity. The metaphors mapped human energy and attention onto battery models, treating personal vitality as a depletable resource that required regular restoration. The mapping was imperfect, human energy being more complex than battery charge, but the metaphors persisted because they captured something useful about fatigue and recovery, about the limits of sustained output. The obsolescence of batteries was programmed through chemistry and design. Every charge cycle degraded capacity slightly. Every calendar day of storage allowed gradual self-discharge. The decline was initially imperceptible, but accumulated until performance fell below acceptable thresholds. Devices were often designed with battery life as the limiting factor, the battery becoming unusable before other components failed, forcing device replacement. This planned or incidental obsolescence created waste streams, economic activity, ongoing markets for new batteries and new devices. The system was economically efficient, but materially wasteful, optimized for turnover rather than longevity. The safety culture around batteries evolved in response to incidents and near misses. Early lithium fires in laptops and phones prompted improved protection circuits, better manufacturing processes, stricter quality control. But perfect safety remained elusive. The energy density that made batteries useful also made them potentially hazardous. The industry accepted some residual risk as unavoidable, implemented multiple layers of protection, established protocols for handling failures when they occurred. The risk was managed but not eliminated, a calculated trade-off between capability and safety that most users accepted implicitly. The democratization of energy storage through increasingly affordable batteries shifted power dynamics in energy systems. Individuals and communities could store their own energy, reduce dependence on utilities, potentially sell stored energy back to grids. The shift was gradual and incomplete, most users remaining primarily consumers, but the capability existed for those willing to invest. The long-term implications for grid structure and utility business models were significant but still emerging. The transition from centralized generation and storage to distributed systems happening slowly across decades rather than years. The future trajectory of battery technology was uncertain in specifics, but clear in general direction. Energy density would increase, costs would decrease, safety would improve, environmental impact would be better managed. But the rate of improvement was uncertain, potentially limited by fundamental physical constraints, by material availability, by economic factors affecting research investment. The optimistic vision was batteries so good and cheap that energy storage became trivial, enabling capabilities currently impossible. The pessimistic vision was progress slowing, batteries remaining expensive and limited, constraining applications that required better performance than current technology could provide. Solid-state batteries promised to eliminate liquid electrolytes, replacing them with solid materials that conducted ions while providing mechanical strength and thermal stability. The solid electrolyte would be non-flammable, removing fire risk, allowing higher operating temperatures, potentially enabling faster charging without thermal management concerns. The solid structure could prevent dendrite growth, the metallic filaments that sometimes form during charging and created internal shorts. But solid-state technology faced challenges in manufacturing, in achieving adequate ionic conductivity at room temperature, in maintaining contact between electrodes and electrolyte through charging cycles that caused volume changes. Silicon anodes could theoretically store much more lithium than conventional graphite, increasing energy density substantially. Silicon expanded dramatically when absorbing lithium, then contracted during discharge. The volume changes causing mechanical stress that fractured the material. Isolated portions from electrical contact degraded capacity rapidly. Researchers investigated nanostructured silicon, porous architectures that accommodated expansion, protective coatings that maintained electrical contact. Progress was incremental. Partial incorporation of silicon into graphite anodes, providing modest improvements. Full silicon anodes remaining elusive despite promising laboratory results. Lithium-sulfur chemistry offered very high theoretical energy density, sulfur being lightweight and abundant, potentially enabling batteries much lighter than current technology. But sulfur cathodes degraded rapidly. Lithium-sulfur cells surviving only dozens of cycles before capacity faded below useful levels. The degradation mechanisms were complex, involving dissolution of reaction products into the electrolyte, shuttling of these products between electrodes during charging. Solutions were being investigated, separator materials that blocked unwanted species, electrolyte additives that stabilized the cathode. But practical lithium-sulfur cells remained years away from commercialization. Lithium-air batteries pursued the ultimate theoretical energy density, using atmospheric oxygen as the cathode material, eliminating the need to carry oxidizer within the cell. The concept was elegant, the energy density potentially rivaling gasoline. But the technical challenges were severe. The reaction products clogging electrode pores, the reactions consuming electrolyte, the need to filter air to prevent contamination from moisture and carbon dioxide. Laboratory cells demonstrated the principle, but with such limited cycle life and efficiency that practical deployment was distant, possibly decades away, possibly never achievable with acceptable performance. Sodium-ion batteries substituted abundant sodium for lithium, potentially reducing costs and avoiding supply constraints on lithium. The chemistry was similar. Sodium ions intercalating into electrode structures during charging and discharging. But sodium ions were larger than lithium, required different electrode materials, achieved lower energy density. Sodium ion cells were suitable for stationary storage, where weight and volume were less critical than cost, potentially displacing lithium in grid-scale applications. Mobile applications would likely continue using lithium unless sodium technology improved substantially. Flow batteries stored energy in liquid electrolytes held in external tanks, pumped through electrochemical reactors when charging or discharging. The energy capacity was determined by tank volume, the power by reactor size, allowing independent scaling of these characteristics. Flow batteries were suitable for large stationary installations, their complexity and weight impractical for mobile applications. They offered very long cycle life, the electrolytes not degrading in the same ways that solid electrodes did. But they were expensive, complex, required maintenance of pumps and seals, had lower energy density than solid batteries. Recycling technology would improve, driven by rising material costs and tightening regulations. advanced recycling processes would recover more materials more efficiently, reducing environmental impact and improving economics. Direct recycling might allow reprocessing of electrode materials without breaking them down to elemental form, preserving the value-added processing that had created battery-grade compounds. The recycling infrastructure would expand, collection networks improving, processing capacity increasing, eventually handling the growing volume of batteries entering waste streams from earlier deployment waves. Manufacturing processes would become more automated, more precise, more efficient. Roll-to-roll processing would produce electrodes continuously, coating and drying and cutting in integrated operations. Assembly would be completely automated, robots handling every step from cell construction through pack integration. Quality control would use advanced sensing, machine vision, AI-driven analytics to detect defects that human inspection might miss. The improvements would reduce costs, increase consistency, enable higher production volumes with less labor input. The integration of batteries into infrastructure would deepen, storage becoming integral to electrical grids rather than supplementary. Every solar installation would include storage, managing the mismatch between generation and consumption patterns. Wind farms would have battery arrays smoothing their intermittent output. The grid itself would transition from operating in real time to managing stored energy, dispatching batteries to balance supply and demand, using storage to defer infrastructure upgrades by managing peak loads, rather than building capacity for rare peak demand events. Vehicle-to-grid integration would allow electric vehicle batteries to serve grid functions when vehicles were parked and plugged in. The aggregated capacity of millions of vehicle batteries could provide massive storage resource, charging when electricity was cheap and abundant, discharging to support the grid during high demand periods. The battery owners would receive compensation for this grid service, offsetting vehicle costs. The complexity of managing millions of distributed batteries would require sophisticated control systems, algorithms optimizing across individual preferences and grid requirements. Second life batteries would extend the useful life of vehicle batteries beyond automotive requirements. Batteries degraded to 80% of original capacity were often retired from vehicles where performance requirements were demanding, but they retained substantial value for less demanding applications. These second life batteries could serve stationary storage, home backup, grid services, applications where weight and volume were less critical. The economics of second life use would improve recycling economics by extending battery revenue while deferring disposal costs. Wireless charging would become ubiquitous, eliminating cables and connectors, allowing devices to charge by proximity to charging surfaces. Inductive charging transferred power across air gaps, efficiency improving as technology matured. Vehicles would charge while parked over charging pads, Phones would charge on desks and tables. Embedded charging surfaces in furniture and infrastructure would maintain device charge passively. The convenience would increase battery-powered device utility while reducing charging anxiety by making charging automatic and continuous rather than deliberate and intermittent. Battery passports would track individual cells and packs through their life cycle, recording manufacturing details, usage history, maintenance events, current state. The passports would enable better second life decisions, inform recycling processes about cell chemistry and condition, support warranty and insurance functions, prove provenance and sustainability. Blockchain or similar distributed ledger technology would maintain the passports, making them tamper-resistant, accessible to authorized parties throughout the supply chain and product lifecycle. Artificial intelligence would optimize battery operation, learning usage patterns, predicting future needs, adjusting charging strategies to maximize life and performance. The AI would balance competing objectives, trading immediate performance against long-term degradation, managing charging to avoid stress while ensuring adequate capacity when needed. The optimization would happen continuously, adapting to changing conditions and usage patterns, achieving better performance than rule-based systems could provide. The convergence of batteries with other energy technologies would create integrated systems greater than the sum of components. Solar generation, wind power, batteries, grid connection, backup generators, all managed holistically to optimize cost, reliability, sustainability. The systems would be self-healing, automatically reconfiguring around failures, prioritizing critical loads during scarcity, opportunistically charging during abundance. The complexity would be hidden behind simple interfaces, users interacting with capable systems without needing to understand their operation. The ultimate trajectory was toward energy abundance enabled by storage, renewable generation producing far more than immediate needs, the excess stored for later use, scarcity eliminated through sufficient storage capacity. The direction was clear, each year bringing incremental progress, each improvement in battery technology making the vision slightly more achievable. The journey would span decades, would face obstacles and setbacks, would require sustained commitment. But the destination was worth pursuing, a future where energy was abundant, clean, stored, available to all, enabling capabilities and improvements that were currently only imaginable. The batteries would make it possible. These containers of chemical potential energy, these devices that stored not just electricity, but human capability, waiting patiently to release their stored power when and where it was needed. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.